Welcome you all. In this session, we are going to discuss in detail about the design of armature in DC machine. So, the armature of DC machine consists of core and winding. The armature core is cylindrical in shape with slots on the outer periphery of the armature. The core is formed with circular laminations of thickness 0.5 mm. The winding is placed on the slots in the armature core. The design of armature core involves the design of main dimensions D and L, the number of slots, slot dimensions, and depth of core. The design of main dimensions has been discussed in the output equation. So now we are going to discuss in detail about the various number of slots, slot dimension, and the depth of core, the armature winding. Let us discuss in detail about this. The armature winding can be broadly classified as concentrated and distributed winding. In case of concentrated winding, all conductors per pole is housed in one slot. Since the conductors per slot is more, quantity of insulation in slot is more. Heat dissipation is less, temperature rise is more, and the efficiency of operation will be less. Also, MMF induced in the armature conductors will not be sinusoidal. Therefore, design calculations become more complicated and core loss increases, commutation interface may occur. In distributed winding, used to overcome the disadvantages of concentrated winding, conductors per slot in distributed is more number of slots. The distributed winding can be classified as single layer winding and double layer winding. In single layer winding, there will be only one coil side in the slot having any number of conductors, odd or even integer, depending on the number of turns of the coil. In double layer winding, there will be two or a multiple of two coils in the slot arranged in two layers. Obviously, conductors per slot in a double layer winding must be an even integer. So here shows the diagram of various types of conductors in armature. Single layer winding and double layer winding has been separately shown. The next parameter is number of armature slot. As the number of slot increases, the cost of punching the slot increases, the number of coils increase, and hence the cost of machine also get increases. As the number of slot increases, slot pitch lambda s is equal to slot width bs plus tooth width bt. Pi d by number of slots decreases and hence the tooth width reduces. This makes the tooth mechanically weak, increase the flux density in the tooth and core loss in tooth. Therefore, the efficiency of machine get decreased. If the slots are less in number, then the cost of punching and the number of coil decrease, slot pitch increase, tooth become mechanically strong and the efficiency increases. The quantity of insulation in slot increase, heat dissipation reduce, temperature increase and hence the efficiency decreases. It is clear that not much advantage is gained by using either two less or more number of slots. As a primary value, the number of slots can be selected by considering the slot pitch, and the slot pitch can be assumed between 2.5 and 3.5 cm. The selection of number of slots must also be based on the type of winding used, quality of commutation, flux pulsation, etc. When the number of slots per pole is a whole number, the number of slots embraced by each pole will be the same of all positions of armature. However, the number of teeth per pole will not be same. This causes a variation in reluctance of air gap, and the flux in the air gap will pulsate. Pulsations of flux in the air gap produce iron loss in pole shoe and give rise to magnetic noise. On the other hand, when the slot per pole is equal to the whole number, pulse of the reluctance of flux path per pole pair remains constant for all positions of armature, and there will be no pulsations or oscillations of flux in the air gap. To avoid pulsations and oscillation, the flux in the air gap, the number of slots per pole should be a whole pulse of plus of. When this is not possible or advisable for other reason, the number of slots per pole arc should be an integer. Number of teeth per pole shoe is equal to 5 and flux passed through 5 teeth. The reluctance of air gap is inversely proportional to the area corresponding to 5 teeth. To obtain good commutation, the flux density in the air gap must decrease gradually from maximum value under center of poles to 0 on center line between two poles, and flux density near the neutral point must be low. A field from the drops off rapidly from maximum value to 0 not only leads to commutation difficulties but may also give rise to noise in machine with slotted armature. In order to achieve good commutation, pulse shoe is designed to cover only certain percentage of pole pitch. The circumferential distance covered by the pole shoe on the armature surface is called the pole arc. The ratio of pole arc to pole pitch is called per unit enclosure, that is per unit enclosure psi lies between 0.6 to 0.7 for DC machine. Thank you.